Okay. Today we're going to get into the final culmination, the final chapter of this course, and that is looking at the geological history of Canada, and later in this lecture, looking at the geological history of Atlantic Canada in particular. And thank you for posing that in the chat. I was just about to mention that. The test results will probably be uploaded later today or tomorrow for you guys. So just stay tuned on Brightspace for that. I'm just finishing up a few things on those. And they should be out soon. They look pretty good, Andrew. I haven't gone through the entirety of the short answer question yet, but otherwise, not bad, not bad. Judging from my other section, which I just finished marking the other day too, that was looking quite good as well. There didn't seem to be any like devastatingly low marks. Everyone seemed to do reasonably well, so hopefully we can say the same for this section. But yeah, you guys are starting to learn how I test and what questions to expect, so that's good. And you know, use the understanding that you gathered from these first two tests and from the first assignments to kind of guide you into the final, because it'll be very similar in structure, very similar in question format. So yeah, and you know, again, please feel free to reach out to me directly through email or during office hours to ask questions about anything, including the assignment, for instance, right? You can run your answers by me if you're not sure about them, and I can let you know, you're on the right track here, maybe expand here. These are the resources at your disposal, right? So, you know, if you completely bomb a question in the assignment, you know, that's unfortunately on you, because I'm trying to give you the resources to help you with that. So hopefully it doesn't come to that, of course, right? I don't want to see anyone do poorly, but you definitely have to, you know, reach out and fulfill your end of the bargain as well in this course. So yeah, keep your eye on Brightspace. All of those marks will be back either later today, most likely tomorrow morning or tomorrow early afternoon, in that kind of ballpark. But I'm trying to get them all done today, so just keep your eye on that. I wanted to show you guys something first before we begin, and that is, I'm going to post this link in the chat. Please open it up and take a look at it in your free time, or just very briefly after we finish today's lecture. It's a really digestible, interesting read about plate tectonics and how it actually began. We kind of alluded to this a little bit before when we were talking about plate tectonics and several lectures ago. You know, I mentioned that, you know, we really don't know exactly how and when plate tectonics got their start and what that primitive form of plate tectonics actually looked like. And so that's still one of the outstanding questions in earth science that's being actively researched today. And we're going to touch upon that concept again. But I wanted to just show you this article quickly here. So this article, when and how did plate tectonics begin on Earth? And it's quite a nice read, some really nice graphics. Some of them are quite similar to the graphics that we saw in plate tectonics. And they go through a whole bunch of unknowns. So this image right here is seismic tomography. And we mentioned this also briefly, basically the use of seismic waves to kind of look into the earth. And in seismic tomography, this is quite important for understanding the architecture of subduction zones. So with this tomographic image here, you can see this downgoing subducting plate here, outlined by this different color as opposed to the majority of the mantle. So you can see this kind of downgoing plate right here, or this plate that's actually kind of reversed in architecture. So this is probably an old preserved subducted plate. Now, on the east coast of the United States, there is no subduction zone, right? So this is some sort of old preserved remnant of a pre-existing subduction zone. So we can use tomography, we can use seismic waves to kind of get an idea of what the mantle actually looks like, because the mantle is very, very heterogeneous, despite what we see in these kind of simplified cartoons of this layer cake Earth. That's generally true, but it's not this discrete layer cake of homogeneous layers. The mantle, like the crust, is also quite heterogeneous. And so this article does a pretty good job of kind of expressing some of these unknowns and some of the contemporary research that's going on right now. So I would invite you to take a read through that if you have nothing to do. It's full of awesome information that kind of puts everything we've learned so far into context. And that's what this lecture today, and basically right up until the end of course, will do. We're going to be putting everything we've learned so far in terms of plate tectonics, orogeny, accretion, structure, into context. Okay, so I wanted to start here with this image. Now, the reason why I chose this image, that's right, Hannah. Yes, Hannah posted something in there. There's only 2 weeks left. So this is our first, or I guess 2 full weeks remaining. And then I think there's like a lecture or 2 into the 3rd week, but we're going to use that as review. So we'll get to review everything we've covered so far. It'll be like an open tutorial session. I'll give you some more information on that in the future, and potential summer field trips as well, which will have to be framed in a SMU external capacity. So it'll kind of be these informal field trips, hopefully, that we can go on. But more to come on that. So the reason why I wanted to chose this image for the opening image of the geological history of Canada. Firstly, did anyone know who painted this? Did you guys know this image? Good guess, but it's not. More from the Ontario region. This is painted by the painter Tom Thomson. Perhaps you've heard of him, a very famous Canadian painter who inspired the Group of Seven, who painted these very surreal, very kind of pastel-y landscape scenes of the Canadian Shield landscapes, primarily in one of the areas that I'm from, well, at least I frequented very, very regularly as a kid, and that is the Algonquin Park area of Ontario. And so this is a painting by Tom Thomson called Jack Pine, and they've actually kind of deciphered using this kind of like landscape forensics to find the exact location Tom Thomson was standing when he painted this image. And this was painted from a location in Algonquin Park. And the reason why I chose this is because this area of Ontario, like the area in northern Quebec and in northern Manitoba stretching up into the territories, is the Canadian Shield, which represents these extremely old, high-grade rocks that represent the heart of the North American continent, around which later continental fragments accreted. So around this area in Ontario and in Quebec and in Manitoba, this is basically the kind of geological heart, the geological continental heart of North America, around which all of the other material, including the United States, Eastern and Western Canada, and Northern Mexico, were accreted against this kind of initial fragment. And so we see these really old, really high-grade metamorphic rocks, felsic in composition, right? These really old continental rocks, which is the craton of North America. These are cratonic rocks, right? Old, stable, continental root rocks. And so I thought it was fitting to display this image. And so as we continue, what we're going to do is kind of walk through the stages of the formation of Canada and we're going to reiterate some concepts that we've talked about so far, like Wilson cycles and accretion. So in this lecture, a little synopsis here, we're going to talk about the important episodes in Canada's geological history, and we're going to kind of break them up into stages. As you'll see, a table for these kind of stages, for organizing these stages, might be very helpful. And I have an example of that in the slides that I'll show you soon. So I do suggest kind of either taking that slide, printing it off, or making your own table and kind of following along with these stages. We're going to talk about continental accretion again and how it built the continent. And we're going to talk about the significance of orogenic belts, right? Orogens, mountain belts, what do they represent? And what's their significance in this capacity? So just to set the stage a little bit, just to remind you of some terms we've discussed already. Craton is the old, often very highly deformed, stable, ancient core of a continent. So very, very old, stable, continental crustal rocks. And when those cratonic rocks are exposed at surface, we call this the shield. So the Canadian shield is not the Captain America shield with a maple leaf on it. It is cratonic rocks exposed at surface. So sometimes these are referred to as basement rocks because they represent the root of the continent, the high-grade metamorphic or igneous rock root of that continent. On top of those shield rocks, so on top of those cratonic rocks, we can pile sediments. So later, younger sedimentary rocks can pile on top of that. And so these sedimentary packages can sit on top of these shield basement rocks, and we call those platformal rocks. So a platform are basement rocks that are overlain by younger sedimentary units. So remember the law of superposition, right? Older rocks are below, younger rocks are above, higher in the sequence, unless everything has been overturned. Rest assured, the entire continent has not been overturned, right? So the law of superposition applies quite nicely here. So if we take a slice through A to A prime, so take a look at that little diagram in the bottom there, A to A prime. What we see are the Canadian shield rocks in green, or gray, whatever that color is, green it looks like. And you can see that as we move southwards, those shield rocks are progressively overlain by thicker sequences of sedimentary units, so platform rocks, essentially. And in the Grand Canyon area, right around where A is, so right around here, right in this area here where the Grand Canyon is, we can see directly down through those sedimentary layers, directly into the basement rocks. So at the very base of the Grand Canyon, we find these very highly deformed metamorphic rocks called the Vishnu schist. And this represents that basement cratonic unit that's overlain by thick sedimentary sequences that we can kind of see like pages of a book through the Grand Canyon. In Canada, in this area of Ontario and Quebec and into the territories, we don't have much sedimentary overburden. We don't have many platformal rocks in this area. You can see some start to accumulate over in the prairies and over into Eastern Canada. But in the Canadian Shield area, this is exposed basement, right? So the numbers here are thicknesses, as you can see in the legend below, thickness of sedimentary units above the basement rocks, essentially. So it's thickening in certain areas, depending on where sediment is accumulating. A province, a geological province, is a subdivision of these cratonic units. Yes, that's right. It's in kilometers, Anna. So 1 kilometer, 2 kilometers, right? Thicknesses. And so a province, geological provinces, are these related subdivisions that are related to each other in either structure, in rock type, in origin. So there's some sort of commonality in a geological province. It's related to each other. It's related to itself in some sort of geological manner, right? Related to either geochronologically speaking, or structurally speaking, or compositionally speaking. And so a craton is made up of many geological provinces that are kind of welded together, right? Welded together through this process of continental convergence and accretion. A terrane is a specific term that we use for a distinct fragment of crustal material that's geologically related to itself in terms of composition and origin, that's accreted onto the side of a continent. So it's basically thrust up against the margin of a continent, much like we saw when we were talking about plate tectonics with respect to Eastern Canada, right? Like the Maguma group and the Avalon terrane, which are basically accreted terranes that were pushed up against Laurentia, Paleo North America, during the formation of Pangaea. Okay, so we're going to use these terms. We're going to refer to these terms as we continue. So then continents grow, as we've seen, by adding material, adding terranes onto their margins. So we'd expect the center of a continent to essentially be the oldest unit, right? The heart of the continent. And we're continually adding material to the margins of these continents, growing the continents in size. This is the process of accretion, right? And through accretionary events, we're always forming orogenic events, right? Because we're basically, this is convergence, continental convergence. So we're pushing fragments into each other. And so we generate mountain ranges, either through continent-continent convergence, like in India and Asia, where you see the Himalayas, continent-continent convergence forming the Himalayan orogeny, right? Or this can also be exacerbated by the formation of continental volcanic arcs, right? Like we see in South America with the formation of the Andes, right? We see an origin there as well, the Andean origin. But those mountains are kind of the result of both accretion and volcanism, right? It's a continental volcanic arc there as well. So when we have convergence, we're forming origins. And there's a question here in the chat. So would the accreted terrane be terrane formed after the split of Pangaea, or did it exist during the time of Pangaea and then ended up accreting? I'm not quite sure I understand, but terranes are accreted through convergence, right? There's no other way you can push something up against the side of something else without convergence, right? So convergence either in the form of ocean continent subduction primarily, right? Where we have ocean subducting underneath continent, and whatever's sitting on top of that oceanic plate that cannot subduct will accrete, right? So this is always a convergent phenomenon. And we form orogenic belts in this manner as well. Like the Appalachian Belt and like the Canadian Cordillera, which is the youngest units to accrete onto North America. Sure. So the evidence that we have from these orogenic belts is very highly deformed rocks, right? Wherever we see very highly deformed, very high-grade metamorphic rocks, this suggests orogeny. This suggests mountain forming, right? There's no way that we could deform these rocks in the manner they are deformed, or metamorphose these rocks to very high grades, meaning very high temperatures and pressures, without being in the heart of an orogenic belt, right? Very deep into the roots of mountains, we have very high temperatures and pressures. And so this influences the rocks, right? This influences the fabric and structure of the rocks. It deforms the rocks, and it can change the composition, the mineralogy of the rocks. And so these rocks can be very highly deformed. So whenever we see rocks like this, and a very high-grade metamorphic rock is called a gneiss. So these are what we refer to as gneissic rocks, high-grade metamorphic rocks. This suggests that this was formed through continental collision, right? Or accretionary events, some sort of convergence. So geologists can use the presence of these high-grade metamorphic rocks to indicate something about the tectonic past of that environment. like in Ontario, in the area that Tom Thomson was painting that painting, those are very, very high grade deformed metamorphic rocks. There's no way we can form those near surface. There's no way we can form those rocks anywhere but deep in the heart of an orogenic belt. And so seeing those rocks now exposed at surface tells a geologist something about the tectonic past, right? This area, once upon a time, must have been an orogenic belt. There must have been an origin here that is now penoplaned, that is now eroded away. And so we're seeing the roots of those mountains now exposed at surface. And so in this image here, we can see 3 different units of rock that have been metamorphosed all under the same conditions, right? So if I had a layer of basalt and a layer of sedimentary rock on top of that, and then a layer of igneous rock on top of that, and I subjected them all to the same metamorphic conditions, all 3 of those rocks would be metamorphosed to the same grade, right? They're all subjected to the same metamorphic conditions in the heart of a mountain belt. And so in this image here, we see these metabasalts, we see metasedimentary rocks, and these metamorphosed granites all beside each other, because that's how they were initially primarily deposited. But now they're all just metamorphosed. And so when I say very highly deformed, this is kind of what I'm talking about here, right? This is a high grade metamorphic rock. Rocks do not form like this primarily as an igneous or sedimentary rock. This very convoluted fabric is a result of metamorphism. And we're not going to get into why this fabric forms and what this rock specifically is in this course. That is a topic for Geology 1200, and I encourage you to take that if you haven't already. It's a great course. And I say that maybe partially biased because I teach it. But this represents a very, very convoluted, very highly deformed, high-grade metamorphic rock. So this is the type of material that we see forming deep in these crustal roots. That's a good question, Hannah. So the scale we probably see here, if I were to have to take a guess, I bet the scale is below that text box. That's probably like a foot or so. That's maybe like 30 centimeters right there, give or take. We can see these on broad scales. We can see these on small scales as well. So just to remind you of this whole process, we're going to be referring to several Wilson cycles here. This is how these continents are growing, right? Through Wilson cycles. And through Wilson cycles, we get this kind of, remember, we get kind of continental rifting, right? And this continental rifting, like we see in East Africa today, will eventually evolve into a marine basin, right? Like we see in the heart of the Atlantic today, right? And so this evolves as a divergent boundary setting underneath an ocean. Eventually, that spreading will stop and the closure of the ocean will proceed. And as that ocean is closing, terrains can be accreted. So we always see these images here that show these really nice ocean basins with nothing in between, like these ocean basins right here, right? There's nothing in there. But keep in mind that in that ocean, we can have microcontinents, we can have volcanic island arcs, we can have seamounts, and all of that material will not subduct. So when the ocean is closing, all of the material that's in that ocean, either in the form of a microcontinent or volcanic island arc, will accrete. And these are how continents grow. And so with respect to Canada, we're going to talk about 4 main stages, 4 main Wilson cycles that led to the growth of Canada. So in Canada, the geological record points to at least 4 Wilson cycles that have grown the North American continent. And this includes essentially 4 supercontinents, if you will: Arctica, Nuna, Rodinia, which we've kind of already talked about a little bit, and Pangaea, of course, which was the most recent supercontinent. And now we're kind of in the middle of a Wilson cycle. We're right in the stage that I circled there, stage 3. And so with respect to North America, we're going to split this up into fragments. And you can see that some of these fragments are numbered 1 through 5. And these fragments added onto the North American continent through this kind of Wilson cycle and accretion process over, the 3 billion years that this occurred. So we're going to start with Arctica. This represents that ancient root of North America. You can see where basically northern Ontario is up in here, and northern Quebec up into the provinces, right? So this is all the ancient root of North America, around which all of these later units accreted. And this was about 2.5 to 1.9 billion years old. Arctica formed. Later, this fragment here was added to this. So this is generating a new supercontinent that's often called Nuna or Nina in Canada, at least. Sometimes is referred to as Columbia in the United States. So, you know, depending on where you are geographically, these may have different names. In Canada, we often say Nuna. And this was essentially the result of a second Wilson cycle that formed a new supercontinent. And now keep in mind that, you know, back in the ancient geological past, you know, let's say 3 billion years ago or so, we don't have a very good constraint on when and how plate tectonics started and what plate tectonics actually looked like. Did plate tectonics look quite similar to how it looks today? Or were these processes slightly different? Were the rates slightly different? What did the plates look like? Plates are in a state of flux, right? So the lithospheric tectonic plates that we have today were not always the same tectonic plates that we had in the geological past, nor will they be the same that we have in the geological future. Plates are also in a state of flux. So we don't really know necessarily what the tectonism looked like back then and when it actually started. After Nuna formed, we accreted the Grenville material here. So this is called the Grenville orogeny, and it's called an orogeny, remember, because this is a mountain chain. And so this would have been the mountain chain that was produced as a result of forming Rodinia, the supercontinent that predated Pangaea, so the predecessor of Pangaea, which formed about 1.3 to 1 billion years ago. And these are the very, very high-grade rocks that Tom Thomson was standing on when he painted his painting. So in northern Quebec, up and even into the Gaspé, and in Algonquin Park, which is right about here, right about there. It's hard to see where I just drew that, but right in there. That represents these high-grade rocks that were at the heart of a mountain belt that was formed as a result of Rodinia amalgamating, much like the Appalachians formed as a result of Pangaea amalgamating. Then we have Pangaea that came together about 600 to 300 million years ago or so, and then started splitting in the Cenozoic, or sorry, in the Mesozoic. So in the late Triassic, early Jurassic, we started to split Pangaea apart again. And now, in the middle of a new Wilson cycle, we've accreted the material on Canada's and the United States' western coast. So this is the newest material to accrete against the North American continent, about 250 million years ago or so. And now we're going to go through each one of these stages in some more detail sequentially. So remember the example from Pangaea, right, from the Appalachians, and we will talk about this in more detail next week. However, just to remind you, all of the terrains that we have here in Atlantic Canada are accreted terrains, right, including the Humber, the Dunnage, the Avalon, the Maguma terrain, the Gander terrain. These are accreted terrains and sedimentary packages that have been thrust up against North America's margin. And in doing so, we're generating an orogeny. Right, we're generating a mountain belt. These are mountains, right? Don't be fooled by this, right? This accretion and orogeny are very related terms, right? Through accretion, remember this is convergence, right? We're smushing terrains up against the margin of a continent, and in doing so, we're thickening the crust. We're thickening that unit of crust. When we thicken crust, we form orogens. Right, we form mountain belts. So this was the Appalachian orogeny. And now this has been penoplaned, right? The Appalachians have been eroded down. especially in this northern area of the Appalachians. But we see evidence of that through the presence of metamorphic rocks and deformed rocks. We'll come back to the Appalachians again later, though, of course. So I want to reiterate that plate tectonics is, now widely accepted and very widely understood with the technology that we can use to investigate plate tectonics today, such as seismic tomography. However, we still don't have a very good control on when plate tectonics actually started. So considering that they may have started in the Archean, this poses a lot of questions, right? It's quite a contentious issue. We don't know, firstly, for sure how continental crust got its origin. Continental crust, and remember when we were talking about plate tectonics a little while ago, I expressed two theories of where continental crust came from. However, there's a little bit of a chicken and an egg sort of problem here with this issue, right? One of the theories states that continental crust began with plate tectonics. As we get plate tectonics, we get subducting crust, we get partial melting through flux-induced melting, hydration melting. That generates these magmas, which can ascend to form magma chambers and then, batholiths, plutons, which represent this kind of primitive continental crust. And so we're developing continental crust through plate tectonics. But how did plate tectonics actually begin? Right? Because in plate tectonics, we have subduction of denser material under less dense material. And so how did that start? The other theory of where continental crust came from is that it formed initially as this kind of thin rind, or potentially through these kind of mantle plume environments like Hawaii is today. So Hawaii is nowhere near a plate boundary. Hawaii is right in the middle of the Pacific plate, and Hawaii is generating vast amounts of magma. And so that magma can feed the surface to form lava flows. That lava is mafic in composition. The mantle is ultramafic in composition, right? So already we're getting a little bit of a chemical differentiation and a density differentiation, right? The material of Hawaii is less dense and compositionally distinct from the material of the mantle. So it's theorized that some of the first continental crust to be produced was rather mafic on average, similar to the oceanic crust. And so maybe the first crustal material to speak of was very similar to oceanic crust in composition, but still of a low density to kind of initiate plate tectonics. Two theories with the advent of plate tectonics is in the modern style we know, right, with a subduction zone pulling down another plate. However, with plate tectonic theory, there is still some unknowns with mechanism, right? Is this plate right here kind of riding over top of that plate, or is this plate down here, the subducting plate, pulling the rest of that plate downwards? Now, it's probably a little mixture of both, but there is a very well-established theory called negative buoyancy theory with respect to plate tectonics. So this states that as this subducting oceanic lithosphere is subducting and being pushed into the mantle, the temperature increases, the pressure increases, and we get this very dense, high-grade metamorphic rock called an eclogite. These eclogites are dense enough to pull the rest of that crust downward. So there's a bit of a negative buoyancy effect, and there's a force pulling that slab down into the mantle. And so it's a bit of a slab pull sort of mechanism related to negative buoyancy. However, how did we produce the first eclogites without plate tectonics? Another chicken and an egg problem, right? How do we initialize negative buoyancy without having plate tectonics to begin with? Because we can't produce these high-grade metamorphic rocks with this negative buoyancy effect without subduction zones. So there's that chicken and an egg problem again. Another theory as to how plate tectonics might have started is related to this kind of drip mechanism, where potentially we're kind of forcing locally plates together, and it's forcing some material downwards. And that material being forced downwards potentially might be metamorphosing into denser rock, which is kind of pulling these sinkers downwards, right? And so maybe this starts to initiate the first kind of rudimentary, very primitive plate tectonic situation. So yeah, it's still a bit of an unknown, and we still have a lot of unanswered questions. And so this is, I think, one of the beauties of geoscience, is that, you know, even though we're studying very, very old systems and very old rocks, the theories are very new, right? There's still a lot to be understood in the geosciences. And, you know, maybe we won't see these questions answered in my lifetime, or, you know, older geoscientists' lifetime. And it might take, you know, your guys' generation to kind of answer some of these questions. It's a very dynamic science. There's still lots to answer. Well, plate tectonics is a theory, meaning it is proven, right? We can observe plate tectonics happening now, but we still don't know exactly how it started. Sorry, I'm answering a question posed in a private chat here. It is proven to be occurring, and we have evidence that plate tectonics is indeed happening, 100% for certain, but we still don't necessarily know its origin, how it got started, right? Mars and Venus don't have plate tectonics. Why don't they have plate tectonics, right? This might have something to do with the uniqueness of Earth with respect to water, the presence of standing bodies of water for extended periods of time. Maybe that had something to do with it. But we still have yet to unequivocally answer that question, why Earth has plate tectonics and how they got started, and why Venus and Mars did not. So there's a lot of contention around this issue, and these are some research. This is some published research that kind of peg plate tectonics, the start of plate tectonics. You can see that it kind of floats all over the Archean. So it is theorized that plate tectonics actually did get its start in the Archean in some sort of primitive way. But there's some researchers that posit that plate tectonics started much later, for instance, in the Proterozoic. So, you know, only a billion years ago or so, maybe plate tectonics in the form we know it got started around then. There's still some contention around this issue in the scientific community. So this is a table that I was referring to. I think it'll be wise to generate your own table and follow along in this fashion, right? So as we talk about these stages, fill in the blanks. And I've kind of done one for you, for instance, the formation of Rodinia, just so you can kind of understand what to expect and kind of what to fill in. I think it's a good idea to do this because we're going to talk about several stages of the formation of Canada. So in order to kind of wrap your mind around these stages and kind of pull out salient information from this material, put it in a table like this. So I'm starting with what I'm going to call stage 0. And I'm calling it stage 0 because Arctica hasn't necessarily formed yet, but the beginning stages have. So stage 1 will be the formation of Arctica. But Arctica formed through the amalgamation of smaller microcontinental units. These smaller microcontinents kind of came together, amalgamated together to form this very first primitive supercontinent that we call Pangea, or not Pangea, Arctica. And that was way down here, somewhere in here, right? Where the very first, most primitive rafts of continental crust are forming. And we have evidence of some of this extremely primitive crust in the form of, for instance, the Acasta gneiss. So the Acasta gneiss is in what's called the Slave Province. And so here's that word, right? Geological province. The Slave Province is a geologically related unit of rock, and it's related to each other in terms of the rock types, the structure, and the origin and development of that unit of rock. there's some other provinces here as well, such as the Superior Province, the Ray Province, as you can see here, the Nain Province, et cetera, right? These are related geological units that, in the case of the formation of Arctica, have kind of come together, amalgamated together. Yeah, it's an unfortunate name, I suppose, and this was pointed out in the chat here in today's climate, but it wasn't named that as a result of servancy. Obviously, it was. I'm not sure why it was actually named that. It was either related to Inuit term in the area, or maybe someone's name who first studied this. That's how the Ray province came to be. The researcher that named that geological province was Ray, R-A-E, and so the Ray province is named after that individual. So yeah, they get their names. However, we just have to separate ourselves from politics, of course, right? We can't let politics dictate the progress of science. We have to be careful with what we do and what we say to a degree, of course, but yeah, it wasn't named that in today's light. But what I wanted to draw your attention to in the Slave Province is that it has the oldest rocks that we know of in Canada and in the world to some degree, for that matter. So in the Slave Province, we have a rock type called the Acasta gneiss. And now the Acasta gneiss in the Northwest Territories is essentially the world's oldest rock at about 4.03 billion years old. And so this is before the Archean, right? Or like right at the beginning of the Archean. And so we don't even know what plate tectonics looked like back then, let alone if plate tectonics was actually a relevant factor in the formation of this rock. However, this rock resulted from the metamorphism of a granitic rock. So this tells us that despite what plate tectonics was doing and what it actually looked like, there had to be some sort of granitic rock around, right? So granites, the rock type that makes up the average composition of continental crust, were being generated back in the early Archean. But not only were granites being generated, they were being metamorphosed. This rock is a very high grade metamorphic rock, right? So how did we metamorphose this rock? Not only does this rock, this metamorphic rock, date to 4.03 billion years, but if this is a metamorphic rock, that must mean that the metamorphic rock must have come from the metamorphosis of a parental rock, right? You can't metamorphose something that doesn't exist, of course. We need a parent rock to metamorphose. So this tells us that there must have been an even older granitic parental rock that predated the Archean, that was metamorphosed to form this 4.03 billion year old metamorphic rock, right? So really intriguing findings here related to the early Earth continental crust formation. The reason that we know the age of this is through geochronology, right? Radiometric geochronology, finding these little minerals called zircon in here, which are very robust minerals. They're very chemically insensitive minerals, so they do not weather very easily. They last a very, very long time, as you can tell. And zircons have an interesting characteristic in that they can uptake uranium and exclude lead. And so once we reach the closure temperature of that zircon, the radiometric clock starts, right? After we pass the closure temperature, as we go below the closure temperature or at the closure temperature, no more diffusion of uranium and lead can occur. And so this is when the clock starts. Uranium decomposes into lead, and we can time that clock by understanding the composition of these zircons. There was a question here in the chat. Maybe Hannah, flip over to public just so I don't have to reiterate that each time. She asks, are zircons the best way of dating oldest rocks on Earth, or are there any other minerals used? Yes, they definitely are the best. They are the most chemically insensitive, they are the most robust, and they're very common. They're common in igneous and metamorphic rocks. And so they're a great tool to date rocks. However, we do have some other minerals that we can use as well, but they can be a little bit more sensitive to temperature fluctuations and chemical alterations. So there are some systematics that we have to kind of pay attention to. And I don't want to necessarily say less accurate, because the date will be accurate, but we do have to understand where that date comes from. Let's say we have a mineral that reaches its closure temperature and then it starts decaying in normal fashion, but then another sort of volcanic event happens, or another metamorphic event happens that reheats that rock. So now that mineral will go above its closure temperature again, and it will be reset. And so the temperature will be accurate, but it'll be a reset clock, because the closure temperature has been gone over again, right? And then came back down. So we need to understand a little bit about the system before we kind of make these broad conclusions. And yeah, so we would, do several dating techniques, for instance, with different minerals in that system, compare them, contrast them, maybe look at rocks that are in the vicinity as well, and compare them to those additional rocks in the vicinity. There's lots of tools that we can use. And so this is the paper, one of the papers that was published relating to dating those zircons in the Arctica gneiss. This is a 2006 paper. By some Japanese researchers, and these Japanese researchers dated the zircon in the Arctica complex, and they found that this zircon, this was from Yilgarn, Australia. So this zircon in Australia now dated to 4.2 billion years. So the zircon itself is older than the Arctica gneiss, but what's interesting about this is that this rock must have resulted from older granitic rock. There must have been rock there to be metamorphosed. And so this just kind of reiterates that point I was mentioning. Okay, so back to stage 0. We're setting the stage for the formation of Arctica. But first we need continental material to amalgamate, to come together, to form Arctica, right? We don't exactly know what the Earth looked like this long ago. We do pretty good jobs of tectonic reconstructions in the more recent geological past, a billion years and later type of thing. But once we get over 1 billion, 2 billion years, we really don't have a good constraint, a good understanding on what the Earth actually looked like in terms of its tectonism. And so we don't necessarily know how all these came together. But we do know that they did, of course, right? We see it preserved today as the North American craton. And so these units, including the Slave Province, the Ray and the Hearn Province, the Nain Province, and the Superior Province, and you don't need to memorize all of those names, but I just wanted to show you that, we have these microcontinents that have amalgamated together. How did they amalgamate together? What process here is at work? What process must have been at work to push all of these continental units together? Right. Plate tectonics in whatever primitive fashion. But more specifically, let's not call it explicitly plate tectonics yet. Let's just call it convergence. Because I'm not exactly sure what it looked like. We don't exactly know what it looked like. Maybe, the beta version, plate tectonics beta version, whatever that looked like, amalgamated this material through continental conversions. And this was about 4 to 2.6 billion years. You can see that there's a pretty big time span here, right? How? This is what I just asked. Continental collision, right? The convergence of these continental units, forming orogens. We have direct evidence of continental collision in the form of what are called greenstone belts. Now, greenstone belts, this is the Superior Province, and we're going to use the Superior Province as an example. So this unit right down here is the Superior Province. Here it is here. outlined very broadly with respect to granites and gneisses in pink, greenstone in green, and greenstone represents a basalt that has been altered or metamorphosed. And so greenstone is mafic material that has been altered. And when that material alters, it forms a green rock, which is why it's called greenstone. I'm going to show you a sample of it in just a moment. The yellow units are metasedimentary rocks. So sedimentary units that have been metamorphosed, okay? Notice the morphology, notice the shape of those greenstone belts here. And we're going to talk about why this is in just a moment, but I want to draw your attention to the fact that they kind of represent these kind of broadly parallel linear units, right? There's these long stretched out linear units separating units of gneiss and granite. So here's, you know, a unit here separated by a greenstone belt from this unit right here. You can see that we have one here separated from this one, separated from this one, right? And in between these granitic and gneissic pink units are these kind of elongate greenstone belts. What does this even mean, right? So to answer your question, Saray, it's not just one big gneissic unit. I mean, there are many subdivisions in here, right? So this is the very broadly speaking. We can have all sorts of different granitic and metamorphic rock types in these units, but in the broadest scale, they're high-grade metamorphic rocks or igneous rocks or felsic igneous rocks. So they're kind of like granitoids, and they can be all sorts of different granitoids, tonallites, monzogranites, granites, diorites, right? All sorts of different granitoids or high-grade metamorphic rocks. But we're not going to go down that road in this course, of course. So yeah, Hannah's touching on it here a little bit, but before that, I'd like to show you what a greenstone looks like. So I think I told you guys that I did some of my PhD research up in the Canadian Arctic, and there's a gold deposit up there called the Hope Bay Greenstone Belt. And so these gold deposits occur in the Hope Bay Greenstone Belt, and it's called a greenstone belt, which looks similar to the ones I just showed you in Superior, because it's green. So look at how green that is. This is a basalt, or at least it used to be. And now it's very highly altered. The reason why it's green is because some of the minerals inside of a basalt can alter to a mineral called chlorite. The mineral chlorite is a mineral that's characteristically very green. And so you can see that a lot of that basalt, which starts its life as a black rock, is now green because of the alteration. You can see that the outside of this rock is very strongly altered. You would really have no way to tell that this is a basalt without, you know, popping it open and taking a look on the inside, because it's just very altered. You can see this kind of beautiful lichen growing on it. It's a very pretty rock just at face value. But you can see that it's very highly altered. You can see this alteration rind around it as well. Right, so very old, very weathered. This rock is about 2.6 billion years old, an old greenstone. So this is why we call it a greenstone belt. This started its life as a basalt, but it's now an altered basalt, a metabasalt, if you will, metamorphosed and altered basalt. And when we do that, it tends to go to this green color. And peridotites, to answer a question in the chat, I'm going to get to that in a few moments, but I have a sample here in front of me. Peridotites, ultramafic rocks that are in the mantle, tend to weather and look like this. So recall when we were talking about the ophiolites in Newfoundland, they look like this. This is the color of them, right? When we saw that satellite image, those hills looked like this rusty brown. That is peridotite. This is what altered peridotite looks like. The inside of that peridotite, you can see, does have this kind of dull, black, kind of gray, green sort of alteration. And so this does not look like what it would look like in the mantle. This is very highly altered. Peridotites alter very easily, but we're going to come back to those. Okay. So, greenstone belts. Notice that they're linear. Notice that they're separating smaller felsic units, granitic or gneissic units. Why? What do they mean? So the significance of a greenstone belt is that, as Hannah kind of alluded to here, it represents units of accreted ocean floor or volcanic arc complexes, island arc chains. So this is why they're kind of smushed out in between microcontinental rafts. Now, take a look at this little cartoon I drew. So this is really, really basic, but it gets the point across. I have a microcontinent here, call this microcontinent 1 and microcontinent 2 in pink, okay? And now we have some form of subduction. You know, remember, we don't exactly know what plate tectonics looked like back then, and you know, the rates and the forces and the mechanisms. But let's just assume this is the case. So now we know there was convergence at least, right? So now we have this subduction and we have this green, let's just use green because it's a greenstone belt, unit subducting under that microcontinent, right? Felsic material, more buoyant than mafic material, it's being subducted underneath. The yellow units represent sediments, either this accretionary wedge sediment here, right here, so accretionary wedge sediment, active margin sediment, or this passive margin sediment right here. This little green hump right here represents, let's say, a seamount or a volcanic island arc complex, okay? In other words, material that won't easily subduct. And so what happens as we converge these two plates? We approach a situation like this, right? They're getting closer and closer. Everything is getting sandwiched in between. Eventually, we have convergence and orogeny. So we sandwich that material in between now. Now we have unit number 1 and number 2, and in between we have the sediments and the basaltic units sandwiched right in between, right? And here's a mountain belt. This is an orogenic belt. Now I peneplane it, and I cut the top of that off. Now I've cut the top of this off, and now what happens if I look at it from the top? It might look something like this, right? We see these smaller units. So here's unit 1, here's unit 2, these microcontinental units, and between them, the material is sandwiched in between. The sedimentary and mafic material that was in this ocean basin, or this basin in between, has now been sandwiched in between the two smaller microcontinental units. Okay, so this is what a greenstone belt is, and it's called a belt because it's this kind of broadly linear feature. And so if we flip back here, you can see that what the superior province actually represents is the amalgamation of even smaller microcontinental units, right? With greenstone and sediments sandwiched in between them. So we're amalgamating microcontinents into larger microcontinents, which eventually will amalgamate into larger continental fragments, right? The growth of continents. Does that make sense with everyone? Greenstone belts. Awesome. Okay. So it's simply the same processes we've been talking about here, right? There's sediments, there's volcanic island arcs. This material will not subduct. And so it's sandwiched in between. It's accreted into this orogenic belt. If we peneplane that origin and we look at it from the top, we see something that looks like this on the slide, right? An orogenic belt in between, which in this case we call a greenstone belt because it's dominated by these altered mafic rocks. And so there you go. That's exactly what we're looking at right here. So there's plenty of evidence that there was active metamorphism and active volcanism during these events, right? If we have subduction of oceanic crust, well, then we get magma generation, right? They're part and parcel. How are we getting magma generation via subduction? Why are these related? Think about that for a second. Not necessarily accretion, right? Because accretion doesn't necessarily generate magma. But how are we generating magma at convergent boundary settings? Exactly, right? Subduction, and then the process of hydration melting, right? Hydration melting takes place. That's how we're generating a magma, right? Through hydration melting, in subduction zones at least. And so when we see these vast volumes of felsic material, of granite, like we see here in Nova Scotia, this is direct evidence for partial melting and subduction. In the in this area, in the Appalachians, this area of Atlantic Canada, we have a large body of granite, the South Mount Batholith, right? If you walk to Peggy's Cove, for instance, or Terrence Bay or wherever, you'll find this granite. You're standing on it today at Peggy's Cove, for instance. That granite only got there because of subduction-related partial melting of that unit, right? Hydration melting. That's the only way it was there. What that granite represents is a fossilized magma chamber, if you will, a frozen magma chamber, right? That magma chamber is now solidified and frozen in the crust. When it was initially forming, this would have been, 5-10 kilometers down in the crust as a magma chamber, which was potentially feeding volcanic vents at surface. And now we don't have any remnants of those volcanic vents anymore, right? We've eroded all of that away in Nova Scotia. And so now we're basically standing on the magma chamber that would have been 10 kilometers down at the time of formation. But the presence of that batholith, the presence of that magma chamber, indicates active magma production. How do we get active magma production? We can't just get it in any old place of the crust, right? We need to have active plate tectonics generating this magma. In particular, we need to have convergent boundary associated magmatism, because at divergent boundary settings, we do not produce felsic magmas, right? So this suggests a convergent boundary setting. And that's why we see the granitic batholith, South Mountain batholith here in Nova Scotia during the formation of Pangaea off the coast of Nova Scotia was a convergent boundary, right? This was a subduction zone around here. And so there was active volcanism in Nova Scotia, New Brunswick, Newfoundland during the formation of Pangaea. And the evidence is right here in the rocks, right? Meteors can certainly give rise to magma generation, but this is a very, very distinct magma generation. We get what are called layered intrusions, these kind of layered intrusions, because we form a basically a pool, a big magma pool that kind of layers and settles out, much like Sudbury, for instance. So very distinct and very identifiable in the case of meteor or meteorite magma generation. So despite the fact that these rocks can be incredibly old, we can still garner some information, primary information from these rocks. So these rocks are about, well, how old are these rocks? These are Archean, so over 2 billion years old, these rocks. But we still see primary features, primary sedimentary features. Look at the sedimentary rock here. This is a sandstone. You can still see evidence of cross-bedding in this rock. Right? You can still see the layering in that sedimentary rock, despite the fact that this has gone through geologic hell, veritably speaking. We can still see evidence of primary sedimentary features there, right? Look above. We see evidence of pillow basalts, right? Archean pillow basalts. And we see the rinds around those pillows. So here's that kind of quenched rind around the pillow there. We can see a rind around this pillow. So really, really old pillows. What do pillow basalts indicate about the formation of that basaltic lava? Volcanism, but where? Was this terrestrial or was this submarine volcanism? Underwater, Hannah pointed out in a private chat here. Underwater. This indicates that it had to be submarine, right? It had to be submarine because that's where we form pillows. We form pillows because they're quenching very quickly in interaction with the water. So right off the bat, right with this evidence right here, we can tell, we can kind of get some information using these primary features where this rock was formed and how it was formed. This rock here is very special. It's called a komatiite. And a komatiite is like a basalt, but ultramafic. So imagine taking some of the mantle, and melting it wholesale, melting all of that chunk of the mantle, and then solidifying it. This is what you'd form, a komatiite. So a komatiite is an ultramafic lava flow. It's an ultramafic lava. So a basalt is a word that we give to a mafic rock, right? A mafic rock as a result of a lava flow at surface. Good question. How would we get an ultramafic lava? If we melt some of the mantle today, say at a divergent boundary, right? Decompressional melting. We partially melt some of the upper mantle, but what sort of rock do we get when we partially melt some of the upper mantle? A mafic rock, bingo, like a basalt, right? So we see a compositional difference here, right? We can't entirely melt the ultramafic mantle because we don't have enough temperature, right? It takes a lot more temperature to entirely melt the upper mantle, but we can melt some of it, some of the lower temperature minerals. We can melt those, but when we melt those and separate them from the upper mantle, it forms a mafic melt. And so you would expect then that a felsic melt melts at a lower temperature, as indeed does. So as we go from ultramafic, mafic, intermediate, felsic, the melting point goes down. So we cannot melt the upper mantle wholesale anymore. Why? What has happened? What has changed? You will never find this rock on Earth forming today. What happens to your cup of tea when you leave it on the counter for too long? Same exact thing happens to the Earth, right? It cools. So when the Earth has formed, when the Earth initially formed back in the Archean, it was much hotter. The Earth was much hotter, about 300 to 500 degrees Celsius hotter in the upper mantle. And so with that increased thermal energy, we can melt some of the upper mantle wholesale, forming an ultramafic lava. But today, the Earth is significantly cooler. And so we don't have the temperature required to form ultramafic melts. We only have the temperature necessary, or the temperature to form mafic melts. So these are very special because we do not form them on Earth anymore. There are locations in Ontario that you can find these preserved komatiite flows in the Superior Province. And they're protected now. You can't go and just willy-nilly sample this rock. They're protected areas because there's only so much of it that we have preserved on the surface of Earth. We don't form these rocks anymore. The interesting texture that you see there is related to the growth of pyroxene and olivine crystals. It's a texture called spinifex, and it's very characteristic to komatiites. Really unusual textures. When we have this kind of cooling ultramafic lava, as it's flowing along, olivine and pyroxene crystals, which are two of the dominant crystals in the mantle, tend to kind of grow in this radiating needle-like fashion. So I'll show you some of that rock right now. So this is komatiite. Doesn't look very impressive, right? Just looks like kind of a ordinary black-gray rock. And it is quite ordinary, but we don't form this anymore. We do not form this rock on the surface. Oh yeah, I have plenty of ultramafic rocks in my office actually. This one here is a komatiite, and it's very highly altered, as you'd expect. And so this is mostly talc now, which is one of the most soft minerals in the that we know of, essentially, right? So it's #1 on Mohs hardness scale, very soft mineral. So you can actually scratch that with your fingernail. Talc, like in talcum powder, exactly. Baby powder is talc. It's a mineral. And so when ultramafic minerals alter in the presence of water, we tend to form this mineral here, talc. And so this is a komatiite. This is an ultramafic lava flow. You don't form these on Earth anymore. I showed you an example of this. Actually, I'm going to grab something here. Just give me a second. So here is peridotite. This is what the mantle looks like. So you can see these beautiful green crystals of olivine and these black crystals of pyroxene. This is what the mantle looks like unweathered, exactly. So this is unweathered, fresh mantle because it's been brought up rather recently in basalt erupting from the upper mantle. And so this is nice, fresh upper mantle. But if we leave this material, because it weathers very, very easily, geologically speaking, if we leave this material for, a couple million years, it'll end up looking like this. This kind of bland, kind of khaki tan colored rock. And this weathering material that you see here is a mineral called serpentinite. And so when these ultramafic minerals weather, under special conditions in the presence of water, we can form another mineral called serpentinite. And so we can form talc as well. So there's definitely talc in here, but there's also this kind of greenish mineral serpentinite. So this is what weathered ultramafic rock looks like. Very, very weathered. And this is from Newfoundland, this one here. So these are from the Table Mountains, from the ophiolite of Newfoundland. And so this is what the upper mantle looks like. And this was sampled from Newfoundland in that ophiolite sequence, right? So you can basically walk right through the moho in Newfoundland. Yeah, so what do we have left here? Okay, so let's just finish up. We only have a couple minutes here, and so I'm going to leave it at the beginning of Arctica, which is stage 1. So we've talked about now the formation of these microcontinents, right? We've talked about the amalgamation of these microcontinents into Arctica. So these microcontinents in and of themselves were manufactured by smaller microcontinental fragments, smaller continental crustal fragments coming together. And we have evidence of that in the form of greenstone belts. So if you're asked a question on a test or a final about the significance of a greenstone belt and what it actually represents, you'd be able to answer it, right? That's what greenstone belts represent. So, direct evidence of continental convergence. So, stage 1 then is the final amalgamation of these microcontinents into Arctica. And this was theorized to be complete, about 2.6 to 2 billion years ago or so, which is when the final accretion of Arctica and maybe even the start of the breakup of Arctica formed. And so now we're floating around right here in the Archean. Okay, so we're moving our way up the geological time scale and looking at these Wilson cycles as we go. And so I'm going to leave it here. Way back here, we had evidence of glaciation. 2.5 billion year old, 2.4 billion year old glaciation. So probably like a snowball Earth sort of situation. That evidence comes in the form of tillites, right? So lithified rocks formed from lithified glacial sediment, till, in other words. How do we know how old they are? Excellent question. It probably takes a lot of sleuth work, detective work in terms of relative dating and absolute dating of zircons and clasts like these granitic clasts that are locked inside of there. But keep in mind that you can erode anything of any age. So dating that granite won't give you the age of the glaciation, of course, right? So we have to use other techniques to date these rocks as well, such as relative age relationships, cross-cutting relationships, things like that. Take a look at the right image. We see striations. Those striations post-date that 2.4 billion year old glaciation. Those are much, much later. That's much later evidence of glaciation. So in that image in the top right, we see two glaciation events, likely separated by billions of years, hundreds of millions of years, right? So the tillite that you see here, that rock that the hammer is sitting on, is evidence of this 2.4 billion year old glaciation event. And the striations you see on the surface of it are a much younger glacial event. Yeah, so we probably had two. It looks like this was the dominant motion in this direction. But there might be some evidence of maybe some ice moving in that direction as well. Or it might just be jointing. It might just be natural breakage in the rock. We want to see repetitive striations. So, but yeah, let's leave it there. I'm sorry if I kind of went off on some various divergences, but there's a lot of stuff in this lecture. We're putting everything together here. We're kind of talking about all sorts of aspects of stuff that we learned about in this course, from glaciation to plate tectonics to accretion to Wilson cycles to structure. So I'm glad you found them interesting. Hopefully everyone else agrees. Any questions, guys? Yes, the date of the final, I believe, is the 13th. But you should always be checking your banner for this. Always check your banner. So sign into your SMU banner, and in there, you'll see all the dates for your finals, for all your courses, the schedules for your courses, all of that. So whenever you're confused about anything related to your final or class scheduling, log into Banner. Okay, that's kind of the end all be all of your course scheduling and exam scheduling. And thank you, Hannah and Youssef, for clarifying there. Okay, well, thanks everyone for